Okay, sorry for the delay. I already used like all my time. Yeah, I'm talking about time structures of model error and DA, and in particular, I'm going to argue that some of it comes from unrepresented multi-scale processes sometime, in particular two-way processes between fast and slow scales in a given dynamical system. We work with Peter Jan as well, and Haunan Ren is our current PhD student. So some of the figures are going to be from his work. Um, so this is the outline of my talk. I'm going to just argue a bit about using finite memory times in the model error of data simulation. And then I'm going to speak a bit about the sources and then summary and current work. So this is some of my notation. Just as usual, we have the evolution equation for our state variables and the observations. And in particular, this model error, when considered, is often taken to be independent from the initial conditions, and I will argue that this is not the case when the so-called memory term becomes important. And also, often we consider this to be, we consider simple structures for this model error. In general, here I'm going to consider autocorrelated model error with some given kind of smooth autocorrelation function, in particular exponential. And the question is, what happens when we prescribe, let's say we have a real imperfect model, but that's describing truth, with a real autocorrelation time scale or memory, and I'm using in the data simulation, when prescribing it, a wrong memory. How much do we get wrong the solution? And these are the two limiting cases that are often used. Right, this is when you have completely independent model errors from time step to time step. And this would be zero autocorrelation, zero memory, versus, and this is often done for simplicity, to consider in one assimilation window all the model errors fixed. That means perfect autocorrelation of one, and we can consider this to be infinite memory. And this is just a simple example to illustrate this. An RA1 process, which is compressive, but you have some model error that is always expanding later, so you end up with a nice stationary process. And just the different evolutions of this process with different memories. So zero autocorrelation in green, more and more autocorrelation until you get to an infinite autocorrelation, and you're basically always adding the same. So the question we're asking is, what happens if in reality you had, and again, I'm talking about a real imperfect model that describes nature. It's something like that. But for simplicity in my DA, I had to prescribe a fixed one, a fixed memory, an infinite memory. This is autocorrelation of one. How badly am I estimating the process? Just a simple illustration. In this simple case, if I take the scalar case, I can show how different memories, when using an ensemble Kalman smoother, impact different time instances in a different manner. So consider that I have an observation at time 3 of the real process, and by using an ensemble smoother, obviously this would be extended in time. K has a component in time. It's projecting back to the initial conditions and the intermediate model states. I want to see how, depending on the memory and depending on the autocorrelation of the model error, the observation will have different impacts in the past. And this is what this schematic is showing. So basically, each plane is, well, first of all, is 4 time steps, initial conditions, 3 time steps, and this very, very, very simple model that I was showing before. And I see that at the time of the observation, well, each plane has, for different model magnitudes, an expansive model to the right of the identity and compressive model to the left. I'm looking at the impact of the observation, so just K. So in green regions, most of the analysis comes from the observation. In magenta regions, most of the analysis comes from the background. And I see that depending on the memory, and remember this is related to the autocorrelation of the model error, the observation impacts differently in very large regions. So if in reality I have a model error which is independent, so I would need to have a k closer to 0, believing more the background. But if for simplicity I use the fixed model error, this is a very large memory, I'm having the opposite effect that I would like to. Haunan then did some this was just a simple illustration in one assimilation window, and Haunan then did some cycling. So this is, for example, a 20-time assimilation window, different number of observations. In particular, here he took 10 observational instances, and it's an ensemble Kalman smoother. And here he played the game of generating truths with given autocorrelations, which are omega real, versus using DA, where the forecasts have an omega G. This is a wrong guess. For a given assimilation window of 20 time steps, and then different time periods for the observations. And this is what this table is evaluating. It's basically this ratio, no? RMSE divided by a spread. So as I was saying, this is the omega is what the true trajectories are generated with versus what the DA is doing. And close to the diagonal, when the true autocorrelation of the error is represented well in the data simulation in this ensemble Kalman smoother, well, we have a healthy assimilation, right? RMSE of the analysis is more or less equal to the spread in the analysis, was a large ensemble size. And on the other hand, we have in the blue areas, this is an under-dispersive ensemble, too much spread for the RMSE, and this is the opposite, too little spread for the RMSE. And we can see that while we get more and more wrong this autocorrelation value, this memory, then problems start to arise. And they are not symmetric, and there is an effect of observational periods, and that's something that Haunan is studying at the moment. But now, where do these different memories, autocorrelation times for the model errors can arise from? And an example is a multi-scale system, and in particular here I'm going to show a two-scale system. So imagine we have a perfect model, and then observations are taken every given number of time steps. And let's say that in this case, in this discrete world in time, case, the time step of the nature is very well represented by the perfect model. And that's very nice. But in general, we have this kind of situation in which you have a reduced model that not only it doesn't agree, we could consider that its time step is a multiple of nature, it's larger, and also it doesn't capture the whole dynamics of all the elements in the system, just a subset. So let's see how errors, components of the model error coming from this mismatch do have different characteristic time scales. I can partition my system in these two parts, a slow variable and a fast variable. And I can think of the evolution for every time step as this partition matrix. So evolution from slow to slow, from fast to fast, and then interactions between scales. Depending on the existence of non-zero matrices in the off-diagonal, then I have complicated or simple cases. If I have no interactions between these two scales, then these diagrams are just showing how information flows So the slow information flows in the slow subspace and the fast in the fastest, so in the fast subspace. Then if I have only interactions from so this is 0, so only the fast feed the slow but not the opposite, I would have this case. And then if the two are non-zero, at every time I have a slow variable contributing to the slow in the next time step, but also to the fast, and vice versa. So different situations arise, and later I'm going to be referring to the following. So in the case of independent evolutions, the future time steps, so imagine the previous thing I had was for one single time step. Now I'm kind of iterating or integrating, but iterating in this discrete case, the transition matrices for t time steps from 0 to t. So in the absence of interactions, I just have a direct evolution from the slow initial condition to the slow final condition. In the case of one-way interactions, I have direct evolution from initial condition slow to final condition slow, plus a component coming from the fast initial condition, and I call this one-way noise. And the worst part is when two-way interactions arise, and I have a direct evolution from slow to slow. We label this memory, to agree with literature, in the sense that you start from a slow initial condition, then there is a matrix that evolves that, but ping-ponging from one scale to another into the slow. Then you have a fast, one-way noise coming from the fast initial condition and two-way noise coming from the fast initial condition. And we partition this like that because they have very different behaviors. So just as an example, a system with two oscillators, a fast oscillator and a slow oscillator, and they are interacting. In the case when the matrices, the interaction matrices are different from 0. So you see that, well, you have zero-way interactions, one-way interactions, and two-way interactions for different ratios of the scales of the slow and the fast. The closer they are, the more one interferes with the other. I'm representing only the slow variables. I'm forgetting about the fast. And you can see how the one-way noise is centered on the independent trajectory. It only increases, it only superposes fast oscillations, but centered on the independent trajectory. But two-way interactions add not only the fast variations, but also a dephasing in the signal, which is particularly important in these two cases. Okay, thanks. I can also represent this in this sort of diagram. So for example, in the one way, I have direct evolution. In these 3 time steps, my final condition is the sum of a direct evolution and these 3 other, which come from the fast initial condition. So these are kind of one-way noises. I'm going to skip this one. The two-way interactions in this path graph representation are clear now. This is the only thing I know, the direct evolution. And this is everything that started from a slow initial condition, but at some time changed into fast and came back. And this here I have the one-way noise in the sense that it only transfers the scales once. And then I have 3-way noise, in this case, 1 plus way noise. This is what I know. This is noise that I can parameterize. This is more difficult, and this is something that I would like to estimate to improve my prediction. So let me try to, using the same system, I would like to separate the components and show how they influence mean and covariance. So this is for the mean. So this is the actual signal, the actual complete evolution in gray. The reduced prediction, the one that started in the slow and ended in a slow. And I see that the fast variations are limited to the one-way noise, whereas the memory has a slow evolving signal. So you see, in this additive case, there is a part of the model error that has a very slow variation, with a large time scale, a large memory. And this fast varying model error has the small memory, so they should be treated differently. And for the covariances, well, after all, the covariances are the ones that are going to be responsible to, to update unobserved variables. If this is the exact one in gray, you can see that the rotation, if the covariance is coming from just the reduced model and reduced with noise, are very different in many cases, sometimes even perpendicular. And the introduction of the memory renders variances that are very, very similar to the original ones. And these are my two last slides. So imagine I have my real process in gray, from which the observations were taken. This looks thick because there are just fast oscillations that I'm not even trying to reconstruct because my time steps do not allow me to. If I have a reduced model and I'm only observing this variable and try to do Kalman filtering, in this case, well, I don't have, my model tends to a fixed point, so there is dissipation. If I add noise from my one-way noise, which I can parameterize, then yes, that inflates the covariances and allows the observations to participate more. But this systematic error caused from the dephasing is not fixed by this parameterization. If I knew the memory completely, then I get almost a perfect reconstruction. And this is, well, if I don't know the memory, if I don't know this evolution operator, in this case I'm only doing a rank 1 reconstruction of that. This is the first left singular vector times the first right singular vector, and forgetting about the singular value, I just want directions of motion. And you get that, this improves the prediction, the data assimilation process, have the background and the analysis. The dotted lines mean that on top of that, you add the parameterization of the fast variation, and that doesn't improve very much. In this case, the slow varying, highly autocorrelated model error was the one that is crucial in this process. And these are my conclusions. So we have been exploring for a while the autocorrelated model error in the Kalman smoother and ensemble Kalman smoother. Guessing the actual autocorrelation of model error can be very, very bad for the performance of the DA system, in particular for shrinking models within an assimilation window. And then we illustrated sources of model error with different nature. And right now we are trying to do some sort of tendency assimilation of fast observations. Differences of fast observations reminded me a little bit of what they were saying about Jeff, but this is in time to try to deduce something about the slow varying model error and separate it from the fast varying model error. And that's what I have. Thank you.
Thank you.
Thank you, Suchi.